What is up, everybody? Welcome to CS 302. Only class of the week because on Wednesday we have Veterans Day. So one time we're meeting, and then the next time we're not meeting on Monday because on Monday we have the second midterm. So today we are going to wrap up our discussion on hashing and basically move on from that, because after the exam we're going to focus on graphs and talk about graph data structures and a couple of algorithms involving graphs. So today will be the end of hashing. However, I have made a bonus lecture available on Canvas related to trees. In this case, to trees. Yeah. No, not trees. What am I talking about? Tries. It's about 20 minutes long, and there's an assignment associated with it that was available for extra credit if you're interested on that. But primarily, I would highly encourage you to focus on preparing for the exam. So today, at the end of this lecture, I will go ahead and make available, it's already configured to be released at 5:30 p.m., a worksheet. And that worksheet will be your primary study guide for the exam, as a lot of the ways the questions are asked there will be asked on the exam. The exam itself will basically cover everything from the last exam to now, which is pretty much all the tree stuff that we learned. So binary search trees, traversals, building a tree from traversals, both from a level order and also from two traversals like in order and pre-order. And then it'll cover Avl trees, and then heaps, as in binary heaps, and then finally hashing. So what we cover today will be on the exam. So without further ado, let's go ahead and finish hashing. And if we have some time after that, I can go ahead and answer some questions on the exam. Otherwise, well then, you can just watch other lectures, I suppose. And remember, I do have the lectures from spring as well, so you can always watch those for extra examples. I don't remember if I did a review for the second test last spring. If I did, the video's there. If not, which I don't know. I don't think I would have, but maybe I did. I don't remember. I think I might have. Yeah, who knows? So to rehash what we talked about last time, we were talking about different ways of solving collisions, and the first method that we talked about was open addressing, which is also known as separate chaining, and that was the one that we were basically building the linked list out of that, or Avl Trees, or whatever it was. From there, we moved on to open addressing, which the other one was closed addressing. I think hopefully I said closed, not open. Separate chaining is closed addressing. The word closed comes in because the address is where you have to hash to. And if that address is closed, it means that you can't go looking for other places. It has to go there, which means that you have to deal with a collision by having a data structure that can maintain multiple keys and key pairs in the same location. So with open addressing, on the other hand, you're allowed to store things in other locations other than where they directly hash to. The big disadvantage of doing this comes when you're trying to search for some data, because now it can be found in places other than when it hashes to, right? So we talked about linear probing, and the concept behind linear probing was that if we're trying to hash somewhere and there's a collision, we look at the next available spot and then insert there. And if it's busy, then we keep checking essentially until we wrap all the way around, and then we know the entire array is full. So then our choices are to reject the insertion or to rehash, which is to build a new array that is, arbitrarily larger, so maybe like twice the size. And then you have to change your hash function, because now, because it's a bigger array, the hash function you have only gives you indices for the old array. So you would never hit the new arrays, at least directly. You might hit them as in resolving collisions, but that would not be ideal. So you need to change your hash function fundamentally to deal with a new array. Typically, you change the modulus to be the size of the array and call it a day. But if you have a more complicated hash function, then you might have to handle that as well. Ultimately, after you do that, you can't just copy and paste like do a for loop and just copy the old array to the new array. You can't do that. You got to take things out from the old array and then put them in the new array by hashing them in. So otherwise, and even so, you have to be very careful about how you do that, so that you don't miss things out when you're inserting, or they get inserted in a different order that might confuse the system. So you have to be very careful how you take one thing out and then insert it, and the next thing and insert it, and so on. Moving on from there, we actually, I think that's pretty much where we ended it there, talking about rehashing and the idea of how to handle a deletion, right? We said that if we, let me actually start with that example. So the kind of the problem we're talking about with deleting was shown here. So like, suppose that we are looking for a number that would hash to 5. So the hash function for this was mod 10. So if we're looking for 85, 65, 25, all these ending in 5, they should hash to 5, to index 5. However, because there's already something at index 5, then you look at the next available spot, which is index 6. So here is the issue. If that spot is empty, you can make the assumption that there's no other numbers ending with 5 found there, because otherwise they would have gone there if they were trying to be inserted and 75 was full. The problem with that logic is that if this spot was full at some point, but then it was deleted, then if you're not aware of that situation, then you might think that there's no valid number there. When at some point there was a number there, which means that the 5 would have skipped that spot and inserted later on, which it did. 55, as you can see, is all the way up in 1. It means that it had to, it had collisions all the way until it wrapped around and got there. The way we fix that is by having to keep an extra value associated with the array. So you can make it a class, or you can make it a separate array. And that can be booleans, just single bit. But the point is that you need to indicate whether something was used at some point or not. So at first you start them out with blanks, initialize the entire thing to zeros. And then the moment that one of those indices gets used, you mark it as used. And there forever, it will always be marked as used. That way, if you're checking for something to see if it's found in the hash table, if you see an empty spot, but you see that it was used at some point, that's the flag that, okay, maybe the number that I'm looking for it was attempted to be inserted here, but at the time it was used, and so it skipped it. So that is how you know, and that is how you solve that problem. So that's linear probing. The advantage of linear probing is that you really maximize the usage of the array. As you can see, it's gonna always fill up. Whereas something like a open addressing scenario like this, you may have like index 5 with 3 numbers, and then something like index 4 with no numbers. So it's a little bit more wasteful in terms of space. However, in both scenarios, this and the other one, it's never a good sign when your hash table is almost full, because that almost guarantees you're going to get a collision. In fact, if a hash table is completely full and you try to insert something else that would not fit, that would be a guaranteed collision, right? So I want to talk about a term called load factoring, and I want to start off the lecture with that. So load factoring is how you compute how full a hash table is. And there's an article from Geeks for Years that can talk about load factoring and whatnot. So here's an example of that. And by the way, if you redeem the extra credit, please make sure you send me your name, like your actual real name, on Discord or Canvas or email, so that I know who to award the points. And then also, I guess I should emphasize, because I had a person send me like their real name, but they didn't tell me who they were on Twitch, and they didn't have the same nicknames. So send me both your Twitch name and your real name, so that I know who's who. Okay? Because like when you have 2 people claiming, and it's like, yeah. But anyways, going over here, if you click on that link, this talks about load factor and rehashing. And the main idea here is that you want to keep track of how full the table is, because the more full it is, the higher the chance that there's a collision. Think about it this way. If your table is half full and your hashing is really good, a really good hash function is going to be almost like random. And by that I'm saying that there's the same possibility that it hashes to one of the indices. Like, it's very, very same possibility. And maybe I didn't say that correctly. A good hashing function is random enough that it should hash to each spot about the same number of times. What that means is it kind of makes it filled out evenly. And that's a good thing because that means less collisions. So the more full it is, again, the higher the chance that there's a collision. But the smaller it is, the less chance there's a collision, but also the more space it takes. So if space is of concern, you need to kind of find a balance between having space available, but not wasting it. And so this is where load factor comes in. Load factor is basically computed with the number of entries in the hash table divided by the total size of the array. So number of entries or items or whatever you want to call it in the table currently, or array, which is called hash table, but it's just an array at the end of the day, in the table, divided by the total size of the array. Just size of array, don't need the word total. I think that sounds redundant. And so, you know, if you have 5 entries in the array, but the array is of size 10, that gives you about half, right? So you get about half a load factor, so 50%. That's a good number to keep it at. Anything higher than that is when you start getting collisions. So anyways, you know, the Geeks for Geeks gives you some kind of introduction into that. But if you Google it, you can find out more about this. I think when like many years ago, when I took a data structure course, they told me to always keep it under 50%, I think it was. So maybe I'll just tell that to you, but I don't know what their claim was for that mathematically. But just know that when people are talking about load factor, that's what they're talking about. So just want to make sure I get that out of the way. So anyways, let's go ahead and talk about these other methods of open addressing. So here's the problem with linear probing. I mean, I've mentioned a lot of problems, but here's another problem, okay? Again, if you have a really good hash function, then you don't have to worry about collisions, as long as you have the space for it, right? But the fact of the matter is, it's a really hard thing to do. So you are going to run into collisions. And that's why we're dealing with this, spending time with this. But what typically tends to happen when you do have problems with your hash function is you tend to see things hashed to the same spots and miss the same spots. So like, if I was to draw like, you know, kind of like a distribution. So let's say we have a hash table, you know, with 10 spots or something close to 10, you know, 0, 1, 2, 3, 5, 6, 7, 8, 9. Oh, that was pretty good. Okay. So what you typically see is like some sort of natural distribution, you know, like the bell curve. That's kind of too thin of a bell curve. But this is what you typically end up seeing when you're hashing things. And what this means is that this region here tends to be more sort of crowded than like this region here. And now you can rotate this around. So like, it doesn't have to necessarily be like, okay, the numbers 3 to 7 are the crowded ones and the numbers 0 and 9 are not. You can rotate the indices around. So like, I could basically say like, okay, I'm gonna basically make this be like index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm not making a statement based on the fact that like, okay, the numbers in the middle get hashed more often. What I'm saying is that regardless of where things get hashed, they tend to be bunched up in this sort of system where like somewhere in the array is more crowded than other parts. This is of course very, very hard to avoid, but it happens a lot, okay? This is, again, like if you take a statistics class, they talk about this stuff all the time. So that's not what I want to tell you. What I just want you to kind of go with is, believe me on this for now, is that things tend to cluster up very often, okay? And it's a good thing for some things, but not for us, not for hashing. So because of that, linear probing doesn't help this problem. Because here's what happens with linear probing. Suppose that I get something right here, okay? What index is this? This index is 9, okay? So that's actually the last index. So this is about to wrap around. Linear probing will start going in this direction, okay? So that means that the next thing to basically insert is gonna get inserted at 0, which already is probably full. Or, you know, maybe like ideally if there's space, there's going to be spaces here. So what that means is that for us to actually find the areas where there's space, we're going to have a bunch of little collisions happening to get there. So like, let's say that this, you know, based on this distribution, maybe the 8 or the 4 are the only available spots. But to find those, I'm going to have a collision here, then collisions here, collision, 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 a bunch of collisions until I finally get to the spot available, right? And the next time I hash something and it hashes here, I'm still going to have the same number of collisions just to get, but in this case, all the way here, right? And that's because it always goes in this direction. It doesn't like magically go this way. So like even if we hash something like right here, we still have to go all the way around to get to this spot if that was the only spot available. So this is an inherent problem with linear probing, that it doesn't solve the problem when you have a bad hash function of overcrowding, okay? And so one of the attempted solutions to mitigate this problem is different kinds of addressing when it comes to open addressing. And different kinds of probing when it comes to open addressing. Instead of linear probing, there's quadratic probing, there's double hashing, and just like there's quadratic, there could be like other n power probing, like what would be after quadratic? Cubic, I suppose? Is that what you call it? Or tetrahedric? I don't remember math terms. But yeah, math people probably know. Tell us if you know. But essentially, what we're trying to say is, okay, if we tend to see that, like, you know, if we have a really big array, we probably end up with these clusters, like maybe a cluster here, and a cluster here, where we have a lot of data hashing to these spots. And that's because frankly, we don't have I mean, again, it's hard, but we have a bad hash function. But again, don't feel bad about that. It's hard to make a good hash function, okay? If it was easy, then cybersecurity would not be this hard, I suppose. So essentially, what ends up happening is we have all these areas that are like overcrowded. We have these spots that like have literally nothing on them. And so what ends up happening is, yet again, something falls here, and it has to basically walk all off this cliff to find a spot that's available and finally get inserted. And then the next time something gets inserted here, so again, it has to walk all the way down. So what quadratic probing tries to solve is saying, okay, if we have a collision here, we check the next spot, sure. If that is busy, then there's a high chance that we're in one of these peaks. So instead of trying to just walk one step at a time, let's make bigger jumps. Think like binary search style, how binary search just jumps to the half and the half and the half. This is kind of like the opposite of that. Instead of making a jump by a single step, we're going to make a jump by 2 steps now. And if we still find a collision, then we definitely know that we're in one of these mountains of collisions. So we're going to make an even bigger step. Maybe instead of 4 steps, we take 8 steps. Or instead of 2, we take 4 and then 8. So essentially, the more that we see that we keep colliding as we're searching, the bigger the steps we take in the hopes to get out of this mess. Then hopefully at this point we'll land here. But it's possible that we take big enough steps we actually skip the entire green zone. That is possible too. But at the end of the day, most of the time, we're going to hit the green zone, and we're going to hit it much faster than checking with linear probing like that. So essentially here, we maybe had to make like maybe 10 steps, and here we only have to make 3. And remember, think of time complexity. Each of these is just a check to see if something is full or not. That takes time. So the less checks, the better, the faster this is. That's what quadratic probing essentially is, and any other kind of probing. We're trying to mitigate this problem with the cluster stuff, and in the case of quadratic probing, what you do is you're taking bigger steps each time to hopefully quicker get out of these condensed areas. And that's pretty much all there's to it. So let's basically you just square or double the value that you get back from the hash. So let us, for example, let's take the same numbers that we did already before. Although, as you will see, this is going to run into some other issues, but that's good. That's good. So let's take these numbers again from the last class. I like these set of numbers because you guys gave them to me. So that means that they're different than whatever example I have from last semester. So yeah, that's good. We want to make new examples. And the next time I teach the class, whether it's remote or not, people will have 2 sets of examples to look at. So, okay. This time around, yeah, I'll stick with making a... I'll stick with still making it the same size. But you'll see that, you know, we're going to have some issues here in a minute. Five, 6, 7, 8, 9. I think I screwed up. I think I made one too many lines. 6, 7, 8, 9. Yep. Okay. It's okay. We'll just erase that. Okay. So, yeah, that'll work. Let's go ahead and hash this the same way. It all starts the same. You still feed it to your hash function, which in our case, we're going to still use the same hash function. And it's going to be hard to show you that this is actually good because we have such a small set of numbers. It's, you know, the thing with things like normal distribution is you only start to see them when you feed enough numbers. But if you don't feed enough numbers, then you might miss things like that. So we'll see how this goes. Okay, so we got our hash function, and we're going to start inserting things into it. So 42 mod 10 is going to fit here. 68 mod 10 is going to go here. Again, everything's the same until you actually run into a collision. So we're not going to run into a collision just yet until we get to the 8. Okay, so this is our first collision, just like it was in any other scenario. However, instead of increasing linearly by 1, we're going to do the quadratic probing. Okay, in fact, actually, before I even touch this any further, let me copy and paste it for other examples. Okay, so with quadratic probing, what you do is you take the shift that you have to do and you keep squaring it, okay? And then you mod it by the size of the array. So what that all means is, let me make sure I remember this correctly. No, you take the index. I think both ways are accepted actually, but I believe it's the index, and you square that. Yeah, it's got to be the index. Okay, so what you do is you feed the 8 through this, and 8 mod 10 is just going to give you 8. And what we're going to do is we're going to take 8 and then square it to some value n, or power it to some value n. And n is initially going to be equal to 1. But after that, n is going to be equal to 2, n is going to be equal to 3, 4, and so on. And so the way you compute the next spot that you want to check in here is this like that? Hold on a second. No, this won't work because we're going to get 8 to the 64th. So no. Sorry. I screwed that up. Never mind. Ignore that. You don't take 8. What you take is just it's 1, 2, 4. Okay, so 2 to the power of 2. Yeah. Okay. So take whatever hfx gives you and add 2 to the n power. Yes, this will work better. Okay. And then you start out with n is equal to 0. Okay, that'll work. Yeah. Okay. So while the other way would work too, it doesn't seem very functional, so I don't think that would be good. Okay. So hfx is where we're gonna get, which it's always gonna be 8. That is not gonna change ever. That's always gonna be 8 because we fed it 8. And if we fed it 68, it will still be 8. Okay? So what we're doing is we're gonna add a certain shift to that whenever there's a collision. Okay? And so that shift is going to be 2 to a certain power, and that's why it's quadratic. So 2 to the 0 power, that would essentially be just 1, right? So the first time that you have a collision, you just check the next available spot. This is the same thing as linear probing. Where it gets interesting is after that, because after that, n is equal to 1. So the next number you're going to check is 8 plus 2 to the first power, which is 2. Okay? So again, that's another check basically right next to that one. And then from there, you go to power of 2 there. So now you're checking 8 plus 4, right? And then from there, if there's still a collision, you would check 8 to the power of 2 to the third, which is 8 plus 8, which is 16. And then from there, the next place you would check would be 8 plus 8 to the fourth, which would be 16 plus 8, which would be 24, and so on. Okay? So as you can see, the indices of the checks keeps growing. Now you should be like, wait a second, but there's only 10 indices here. Right. You gotta take another mod function on this to figure out where that would actually store at. So initially, where you would try to store is, like I said, at the index. So that would be 8, and then 9, and then 10, and then from there it goes to 16, 24. Are those numbers right? Let's see, 8 to this 8. So it would be 8 plus 1 is 9. Well, this is where you first have the collision. So this is the first one, 9, and then 8 plus 2 to the first power, which is 2. So that would be where the 10 comes from. This is to the 0 power. So the first power, and this is to the second power, which would be 4 plus 8. 4 plus 8 is not 16 though. 4 plus 8 should be 12 actually. And then from here, this is to the third, so 2 to the third is 8. So 8 plus 8, this is 16. So there we go. These look more right. It should double every time. From here, right now we have a shift of 4, so now we have a shift of 8. So this should be 24. And then here, this will double now. So this gap here increase was 8. This gap should be an increase of 16. So this would make it 24 plus 16 essentially. So 40. Now, is that the same thing we would get? 8 plus 2 to the fifth. This is 32 plus 8. So yeah, that's right. Okay. So these are all the checks that we will do. Now, what we got to do is we got to take the mod of these. So this would still be 8. This will still be 9. This will be 0 though. This will be 2. This will be 6. This will be 4. And this will be 0. So those are all the numbers that we're going to check. The idea here is that we get further away quicker than with linear probing. Again, this is a really small array, so it's kind of hard to see that. But if it was a bigger array, like size 100, then you could see that a little bit better. Because if it was size 100, you can see how quickly we get away from this area. So let's say that the really cluster area is from like 5 to 20. This is like the busy area, okay? If we were doing linear probing and we were supposed to hash to 8, we'd have to go all the way from 8 to 21, which is the next available spot, right? That's a lot of checks. In fact, you know, that would be basically 12, 13 checks that we have to do, right, to get there. With quadratic probing, we would get there right here, which would be 1, 2, 3, 4, 5 checks, right? So the 6 checks. So essentially, 6 to 13, we're saving half of the checks. But if we went ahead and changed this to say that the busy zone was like from 5 to 40, or let's say 39, I suppose. In this scenario, we gotta do 34 checks. Whereas here, we just gotta do 1, 2, 3, 4, 5, 6, 7 checks. 34, 7. See the difference there? It starts to get bigger. So quadratic probing is useful when you know, it's easier to see this when you have a bigger array. But you get quicker out of the crowded area. Okay? So, but anyways, in this scenario here though, we actually just go ahead and insert the 8 right there and call it a day. The 47 does get inserted right here. And then the 96 does get inserted here. The 0 gets inserted there. 23 gets inserted here because we have 1 check. And then where are we at? I lost, 23. So now we got to do the 55. This will be interesting. So the 55, we'll first try to go here. Then it'll try to go there, right? Because it'll be 5 plus 1. And then 5 plus 2. And then from there, it'll be 5 plus 4, which should be 9. So the next check is going to basically be all the way here. And then that's still a collision. So now it's going to be 5 plus 8, which is going to be 13. That would be wrapping all the way here to the 3. So that is still a collision. So that's, you know, it's like a big arrow that goes away like that. And then from there, you go ahead and do 5 plus 16, which would be 19. That's still a collision. So then you do 5 plus 32, which is going to be still a collision because it's here 7. And then 5 plus 64, that is still going to be a collision there. And then 5 plus 128, which is still going to be a collision. 256. All right, finally we get one, so that's not a collision. 5 plus 256 is going to be 261. So finally that gets put there. So here you have sort of the opposite scenario, right? With linear probing, you could guarantee that everything was going to get full. With quadratic probing, you have two sort of bad scenarios. One of them, like now, it's possible that when things are almost full or like, you know, really, really close to being full, with quadratic probing, you might never even find the spot, You might keep skipping it. Like imagine that like it's an odd it's like an odd number and you're like, you know, you're adding even numbers or things like that. So like there's no feasible way of finding it. But like if here, the only reason that we actually finally got it was because we're adding an odd and even number. But if the number we started, like if we're looking for something, you know, at 4 instead of 5 initially, and the last spot was odd, we would never find it, right? We would literally never find it. So like imagine instead of inserting a 55, we try to insert a 54. We might never find that one because we keep adding just even numbers because it's a power of 2. So it is better. In fact, literally almost the entire array, like all the odd numbers, could be literally empty, and we might never find them because of the same scenario. So that's one of the disadvantages of quadratic probing, that it solves the problem of basically overcrowding, but you might never actually use some of the spots available. Or what would happen here, it might take a lot of iterations. You basically keep spinning around the table like 50,000 times until you actually find the spot. But there's no guarantee you will even find it, like I said. I actually probably missed it because 5 plus 16 was 21. So I don't know what happened there. But yeah, we probably should have found it there. But anyways, imagine that we skipped that number, okay? Oh yeah, you guys said it over there in the chat too. I didn't see it. My bad. So yeah. But anyways, the point being that quadratic probing does have that issue. How you solve that issue? Load factor. You know, you basically rehash this so that it doesn't get so full. So you know, that actually is a general solution to overcrowding, actually, not just quadratic probing. But that's kind of the pro and con with quadratic probing. The pro being it solves overcrowding a little bit. The con being that you may go back to the situation that we started with, which was you can't take full advantage of the array anymore. The way that I did it here, where you're squaring the hash, is one way to do it. The other way that I've seen to do it is you just double each spot from the index. So like, you know, if this is where you hash, then you check 2 from there, and then from here you go 4, and then 8, right? The way that I did it is basically go 2 from here, 4 from here, and then 8 from here, right? So these are 2 ways of doing it. There's no right way or wrong way, so either is fine. So, you know, you might still be asking yourself, like, why are we doing this when separate chaining works? Because there's some scenarios where this might actually, you know, space might be really of a situation of importance. But finally, let's talk about double hashing. So this is still a form of open addressing. And in fact, what I've shown you so far is a form of double hashing, right? Because linear probing is nothing more then taking h of x, whatever that value is, adding 1 to that, and then computing a new value from that, and then feeding that to the next formula, and so on. We can call the second hash the g of x. So double hashing is basically you use two hash functions. One of them is to first try to map something, and if that fails, then you take that number that you got from the first hash function and you feed it to a second hash function to find the next spot. And you could potentially have like triple hashing if you wanted even. The idea being that instead of sticking to something like linear probing or quadratic probing, where it's like a defined, formula that's very simple, like 1 or squared or whatever, you use a custom formula that you think will, like you obviously you're trying to avoid collisions, but if you do get collisions, then you come up with a really nice formula to avoid follow-up collisions. And so, if we were to represent linear probing with double hashing, it would be something like this. If we were to represent quadratic probing with linear hashing, it would be basically kind of what we drew before, plus 2 to the n power, or to the I power, right? You could also write it like this if this was the number of collisions you had as well. So either one of those would work as well. Okay, but essentially that's what double hashing is. So in practice, what happened to my numbers? Oh, here they are. Just bring them beneath this, and then let's bring this up. Like that. Okay, cool. All right, so in practice, what that looks like is, let's say that we're going to have a second hash function that is going to be g of x is equal to h of x plus 2. What does that mean? That whenever I have a collision, instead of checking the next available spot, I'm going to go ahead and check 2 spots ahead. No, that's not that good, because what's going to happen, I'm going to miss all my odds or even spots. So maybe I go ahead and subtract. Well, I can't do plus 2 minus 1. That would just be the same thing as 1. So as you can see, it involves critical thinking as well, just like a normal hash function would do. But I can't really think of any other hash function to use other than adding or subtracting things. I mean, I guess we could multiply. Yeah, why don't we do multiply? Let's multiply it times 3 plus 1. Just cause. That'll give us some interesting numbers, I suppose. Okay? And so why are we picking this? Again, you want to pick something based on your data. So a lot of the times when you're, actually I don't want to delete those because there's no collisions there. A lot of the times when it comes to picking a hash table, a hash function, it depends on the data you're working with. If you know that your data is always ending in like 5, you definitely don't want to pick your hash function to be something with like mod 10, because that's just going to always hash to 5 and you're going to get clustering, right? But then you might be able to look at the second digit, the second significant digit, because maybe that varies a lot. Or you might look at something as a combination, like maybe you take the first digit and the second digit and you multiply them together, and then bam. You could totally make that be your second hash function, by the way. Just take the numbers and multiply them together. Like take 4 and 7 and multiply them. Or for the single digits, take like 0 and 8 and just multiply them and then add like the same number again or something. I don't know. The point being that it's up to you based on the data that you're getting. And it's not, you have to experiment. What if g of x fails? If g of x fails to find a valid index, what you have to do is the same thing you have to do if quadratic probing fails, or if linear probing doesn't find a spot because it's full. You have to rehash. So that means you have to make a bigger table and you have to change your hash functions, which at the most basic level means you have to change the modulus part. But if you're actually using sophisticated hash functions, then you have to reinvent the wheel essentially. So yeah. Not the best of solutions, but all right. So in this case, let's see if our ghetto hash function will help us do better. So 8 is the first issue that we have. So in this case, we are taking 8, multiplying that value directly times 3. So 8 times 3 is 24, plus 1 is 5, and then I guess I forgot. We probably want to. We do still want to do some kind of modulus operation at the end of this, so that it still fits in the table, right? Otherwise, it goes out of bounds. So we'll just take mod 10 of the whole thing. So 8 times 3 is 24, plus 1 is 5. Mod 10 is equal to 5. So we have a collision there. So that wasn't maybe the best one, but oh well. All right. So what do we do then? Well, we got to rehash. So how do we rehash? Maybe make a table of size 20. So why not? Let's rehash. We haven't done any of those. So in the rehash, 10, 11, 12, 13, 14, 15, 16, 17. Whatever. We'll just stick with 17. So in the rehash, you know, we're going to say we're going to modify our hash function to, you know, be 20 here, and then technically speaking, we should modify this to be 20. But I think if we do that, I think we're gonna run. We're not. Oh my god, that's gonna make the math difficult. Oh well. I was gonna leave this at 10 just to show you, but you really would never leave that at 10. By the way, another thing you can do with the double hashing is you can treat it like probing, where what you're hashing is the value. So like, let's say you feed it to itself. So we could actually do this with this example. So like, let's say we get the 8 times 3 plus 1, and that gives us 5, right? We can feed that 5 again to the double hash. So we can do again, like, then we can take 5 times 3 plus 1, which would be 15 plus 1 is 16, which gives us 6, which is available. So that's another thing we could do, by the way. So you can keep feeding the value, just like you would feed in quadratic probing the value itself. You can keep doing that to keep trying to hope to find something, until, again, like linear probing or quadratic probing, you give up, right? And quadratic probing is a lot harder to figure out, because with linear probing, you give up when you basically wrap around. With quadratic probing, there's a chance that you could potentially keep looking for like ever until you find something in like the 20,000th iteration or something. Well, mathematically, that's not going to happen, but you know what I mean. You could do a lot more checks, right? So actually, before we rehash, let's try to use the second method first and see if we find any success. So we'll keep this at 10. Sorry for the change of notation from mod to percent, but I just ran out of space to be able to write the word mod in there. So anyways, if we do that system where we keep feeding the result over and over, then we do find that 8 can actually go here. The 47 will go here, but then the 96 is at collision. So let's feed 96 times 3. What is that equal to? That would be 300 minus 12, so 288. Plus 1, 289, mod 10. Ooh, okay, we got lucky. It actually goes there. The 0 goes there. 23. Oh, that's a collision. That's really putting to limitation my multiplication motivation for the day. So 69. Yeah, I should have just been able to do it in my head. That's it. Okay, 69 plus 1 is 70. That is a collision. So let's take 70 and multiply that times 3. 210 plus 1 is 11. So, okay, that actually fits there. So, what number is this? 23. 55. 55. That's going to be a lot of collisions before we probably find the 4 out of that. But let's try. 55 times 3 is going to be 150 minus 15. So that would be 135 plus 1, 136. Correct me if I did the math wrong here. That is not good. So let's multiply that times 3. Oh, man. So that would be 18,190,14. So 408 plus 1409, I think. And then times 3. That would be 1200 minus 3. Or sorry, no, plus 27. So 1227 plus 1, because of the 1, that would be 1228. Yeah, so you guys can plug that in the calculator and let's see if we ever find a solution. So 1228 times 3 plus 1 is equal to 3685 times 3 plus 1. That's ends on 6, 11,000 times 3 plus 1. That ends on 9 times 3 plus 1 ends on 8 now, times 3 plus 1 ends on 5. If we were math people, we could probably find a pattern to this and figure out if it's never going to fit or how many times it's going to take to fit. Let me do it like 3 more times and see. We got an 8, we got a 5, we got a 6. Okay, so I've already gotten to basically 217 million, and I still haven't found a solution. So I'm going to go ahead and say that we have to rehash at that point, okay? So that would be the point when you would rehash. So you guys go and figure out if that would work. But anyways, let's rehash since we have a little bit of time. So when you rehash, let's say we make it this big. You got to reinsert everything from start, okay? You cannot just copy and paste the index around. That will not work. And the reason why that will not work is because things may not hash to the same spot anymore. Also, something I haven't talked about, when it comes to deleting or searching in something like double hashing or quadratic probing, it's quite tricky because you have to do the flag thing again, like the deleted flag. You have to keep track of that, and you have to keep going until you either find an empty flag or you have like you basically give up. So it's not easy to figure out whether something is. I mean, you might as well just do a linear search at that point. Like you might just go and do linear search in the array, because otherwise you could be there forever. Could you add a random element to g of x? No, you cannot. That brings up a really good point, actually. So here's the thing. The fundamental thing about hashing. Sorry, I was thinking of the right word. A hash function has to be deterministic. I believe that's the right mathematical word. I have it actually written down somewhere here. I was going to talk about that when I was going to get to cryptographic hashing. Yeah, here we go. So deterministic is indeed the right term. So a hash function has to be deterministic. And what that means is that whenever you feed it a number, it will always map it to the same result. So that means if I feed it a potato, whatever it interprets a potato as, if that gets mapped to a 5, then a potato will always get mapped to a 5. If I feed it my dog and it maps to an 8, then every time I feed it my dog, it's going to always map to an 8. That's a fundamental thing with hashing, because that's the only way that we can know whether something is stored in the hash is actually found there or not, right? So if you go back to something like separate chaining, which is a more practical use of hashing that you would see in the real world. If I put a 55 in there, it gets stored on 5, right? On index 5. If I'm looking for 55, if it's stored in there, like later on, to check back tomorrow, I see if it's 55 is still stored there. 55 hashes to 5, which means that it has to be in index 5. And if it's not there, then I can guarantee you that it's not there. That is because of the deterministic nature of the hash function. If it's not, if it's random like you say, then today I feed it the 55 and it gets stored in 5. Tomorrow it gets stored on 8. That gives me no guarantee of where it's stored, which essentially means that it's useless for retrieval information. You might as well just store the entire data in an array that's unsorted, like in an unsorted linked list, because at that point you've destroyed the purpose of a hash table, which is to be able to store data and then retrieve it quickly, right? Remember, why are we doing hashing? Because we had this fight since 202. We want to be able to insert fast, we want to be able to delete fast, and we want to be able to access things fast, right? or in this case even, search things fast, more than access to search things quickly. With a hash table, with a perfect hash, which by the way, the term perfect hash means that there's no collisions. It's like you have the perfect hash function that will never have collisions, such as like a direct access table essentially, but also I guess a really darn good hash function. With a perfect hash, you have O of 1 insertion, O of 1 deletion, because you will never have a collision, which means that there's always only one item to look at. So O of 1 deletion time, a constant time for those. And then access time is O of 1, and search time is O of 1 as well, because you just feed it in the hash function. It immediately gives you an index. You look in there immediately, and immediately know whether it's there or not with a single comparison, which is to what is located there, right? Or in fact, if it's even, you don't even need to store the number. Okay, that's the other thing. You know, if I know that I have a perfect hash, I don't even need to store the numbers. I can just mark the spot as full, and that guarantees that this number is there. And this is something actually used in cryptography and whatnot. So like, if I know that I have a perfect hash and I look for a 55, and I know that that's the only number that could ever get mapped to this index of 5, big if, then I don't even need to store the number 55 in there. I just need to store the fact that it's full. Just a little check mark, a little single Boolean. So you could actually store more data in your table than it would normally fit. So like, think about like in terms of like integers, right? So all these numbers, imagine that we built the perfect hash table for these numbers, okay? You could do that actually if you make it size 100. So you make a hash table of size 100, right? So these numbers, they all take 4 bytes each, right? Because they're integers. You can probably put them in the short, but whatever, 4 bytes each. I store them in a hash table, and in the hash table, I need a single bit for each of the indices. A single bit. Remember, there's how many bits in the byte? 8 bits in the byte, right? So, and there's 4 bytes for each of these. So if I got an array of size 100, that's 100 bits. That would be 100 divided by 8. That's 88 for 11, and then about 13. Okay, so you need about 13 bytes. Okay, so 13 bytes, basically the equivalent of storing just over 4 numbers, right? Four numbers plus 1 byte. So let's say about 5 numbers, less than that is what you would need to store it, right? So essentially, in the same space that it takes to store this much, I can store this much data, right? Plus whatever the you know, how much code it takes to store the actual hash function, because you got to store that too, right? So there you go. You just invented compression, or at least a form of it. So anyways, hopefully that answers your question about determinism. Well, not about whether you can use random or not. And the question is, you don't want to. You don't want to use random. So that kind of segues into the thing about cryptography and not cryptography, but cryptographic hashing. But before I do, I want to see if there's anything else that I want to talk about here. I think I have a table of pros and cons, which I pretty much mentioned already, but I want to make sure. Yeah, I pretty much talked about most of this. Yep, okay. So let's actually move on into that. So this is kind of like a bonus thing to talk about this. And that is the idea of like hashing for security, okay? And I'm going to post a link here, and I'll post it on the description, that I encourage you to check out. It's pretty cool stuff, actually. And basically, one of the ways that we store things safely in the computer is with hashing. When you log into your computer, you know, you put in your password, your computer could store your password in plain text to match it, you know, do like a little string. If A is equal to B, and B is the string that you typed in versus A, which is your password stored somewhere in memory in a file, then you let them log in. What is the problem with this? The problem with this is that if somebody gets access to the file that has the password in it in plain text, they have your password. And I bet you they don't just have the password to that location, but you probably use that password in 10 other websites, probably a bank account too. So not a good thing, right? So what do? You use a hash function. Because what does a hash function do? It takes information and transforms it into something else. And if you do a good hash function, it's very hard to see from A to B. It looks like something random when it's absolutely not, but it looks random. And that's a good thing, because we call that a hash. And the hash is basically the result of feeding input into the hash function. So before, when we were thinking of a hash, we were thinking of indices, right? Indices that we're trying to store. But now I want you to think of the hash itself. The index value is just the value that we're looking for. So for example, if I feed it the word Mario, that Mario is going to be converted into a really, really big number. You don't even keep the number in decimal. You keep it in hexadecimal. And that's how most of the hash functions work for security. Here's the other cool thing. It's very easy to map something, the input to the output if they're the same length. But a good hash function will return a number that is about the same size regardless of the input. You could have fed it 1 character or 20 characters. It would still return to you something of like 100 characters long. Again, we are not storing any data in the hash table. What we care more about is the index that it hashes to, the hash itself, the value that we get from the h of x function. So what makes a good cryptographic hash function? And so that's kind of what that article talks about. There's a couple of properties. There's 5 properties that they mentioned, and I kind of want to go over them. The first one we already talked about, deterministic, which is, if I'm going to store my password and that password gets hashed to a certain code, a bunch of letters, they always have to be the same letters. Because here's the thing. Now, in your computer, instead of storing the password in plain text, you're going to store the hash value. And then that hash value is very hard to be able to see what it originally was. And so now it's a little bit safer, because if somebody steals that hash value only works, when in this specific instance, when the hash function like pops it out. But it doesn't mean that if I feed the hash value into the hash function that I'm going to get the plain text password. It just means that if I can feed the hash value directly to the computer, yes, I can get around, I basically cracked your password, but only in that system, but not in other systems as well, because I don't have the actual plain text password. Okay, so that of course is because of the determinism. So you want to always get back the same hash from the input. So if I give it my password, I want to always get the same combination of characters. So that's the first thing that makes a hash function important. And it's not just for cryptography, but also in general. You always want those hash functions to be deterministic, which means no randomness at all. The second property, and this goes more into cryptography, but it's also useful to have in general hashing, is quick computation. What it means is that it's useless for you to have a hash function that is so beautiful. It always like makes things be super even. Like it almost feels like it's random. It has like beautiful distribution. But guess what? It takes like 10 years to hash one value. Not quite useful when you're trying to log into your computer and it takes 10 years to accept the password or not. There's a limitation. Some say that it shouldn't be immediate. Some say that a delay is actually a good thing, to avoid brute forcing attacks and things like that. But there's a line you're gonna draw. Okay, 1 second, I'm okay with waiting. 1 year, not okay with waiting. But if it comes out, I'm using hashing for actual like coding, then I definitely want it to be super fast, right? So quick computation is something to consider. The third property is known as pre-image resistance. Pre-image resistance is the idea that if somebody steals from your computer that hash value of your password, it should be very hard. In fact, it should be almost impossible, but not fully impossible. That's why, in fact, they use the word infeasible instead of impossible because, as we've seen more, over and over time again, things are meant to be broken and they will be broken given enough time. So pre-image resistant is the idea that if you get that hash value, you can't convert it back to the original input value. So given h of x, you cannot get the x out of that, right? So if you get the h of x, which is what the hash function gives you, you can't kind of look at that and then like discover what the original input was. Why is that important? Because if your hash value, if your hash function, if your hash gets stolen, you don't want the hackers to essentially look at that and then like feed it to some magic machine and then get your plain text password of that. You don't want them to reverse the process. That's what pre-image resistance basically means. Okay? And again, use the word infeasible because at the end of the day, that hash function is just math. And if they can discover the math, it's like imagine that you use something like a Caesar cipher. That's rotation 13. So you take each character and you rotate it 13 spots in the alphabet. So like an A becomes like an M or whatever the 13th letter is. Okay, given enough passwords, given enough A and H of A or X and H of X, I'm going to very quickly discover that all you're doing is just rotating your characters. In fact, there's some software that I remember when I took the blockchain class with Dr. Kim that he told us some software to download that would crack a bunch of passwords very easily, and one of them was rotation 13. It was just like, yeah, no, like you give it like a sentence and it would be like, yeah, this is rotation 13. So that was actually pretty cool. I wish I remember the name of that program. I'll have to rediscover that for my cybersecurity course that I'll teach eventually. But yeah, so you want to make that process be very hard, and that's what pre-image resistance is. Okay. The fourth property is known as the Avalanche Effect, and the Avalanche Effect is meant to protect someone from again trying to discover the transition from X to H of X. And what it does is basically, one of the things that a hacker tries to do to discover what the hash. So here's the thing: the hash function is very important. If you know what the hash function is, then it's over for the most part. It's like relatively over, but not always. So what you want to do is you try to map. You're like, okay, what happens in this mystery box that gives me H of X? Is it rotation 13? Is it something more complicated? MD5 checksum? What is it? What is SHA-2? What is happening in there? So what do? You study the inputs. So you start feeding it. Let me feed it an A. Let me feed it a B, a C, a D, an E. Maybe feed it the word high. Feed it a bunch of words and start analyzing what the output is. You start to find patterns. Imagine that the hash function that you do is cool, but it always returns the same length as the input. So if you feed it 3 letters, you get 3 what looks scrambled, but still 3 letters here. It's not going to take long before people start to map and see that, okay, when I feed it this pattern, I'm always getting this combination on the scramble here. So you start to connect the dots. Given enough of that, given some AI, and this is what that program that I was talking about did, you basically map that and then crack the hash function, right? That's essentially what the Avalanche Effect avoids if you do a good hash function. The idea of the Avalanche Effect is that no matter what variable input you have, a tiny change in your input. So like if you feed it like 10 letter A's, too many, okay, 6 because I don't want to write 10. And then you feed it the same input, but you change a single letter here. When you're looking at the H of X of that, this and this, in a bad hash function, they would be very similar, which would lead the hacker to discover what happens when an A becomes a B. What the pre-avalanche effect is saying is, even a tiny change should make these completely different, like totally different. That makes it very hard, because then, if you also feed it something completely different, so like you feed it like a bunch of Y's and T's and whatever, this also gives you something totally different. And so now, because 1, 2, and 3 are totally different, nobody would figure out that these two are super similar, because that it doesn't guide it that way. So that's what the avalanche effect is talking about. You want to make your hash functions just look like it's random. Like it looks, it's not random, but it just feels random. And again, when you're dealing with just in general hashing, not just cryptographic hashing, this is something really good to have, because that's what's going to avoid you from clustering things if you have the avalanche effect. Because again, clustering might happen because you have a lot of numbers that are close together, so they get hashed, they get put together again. But with something like the avalanche effect, even if they're close together, as long as they're slightly different, they're going to be sent to totally different spots in the hash table, which is a good thing for you to avoid clustering. So that's something that is shared between cybersecurity, cryptographic stuff, and general hashing usage. Finally, you have collision resistance. Collision resistance is a little bit trickier to explain. The idea being that, well, actually, no, it's not that hard. Think about collisions that we have it, Here's the problem. Imagine that you're using a numerical password, and you have 55 and 75, right? That we were using earlier. And your hash function is like omega lol, just still not 10, even though this is like some cybersecurity thing, okay? The problem is this. Somebody tries to log in with, sets their password to 55. Of course, the value that is actually stored is 5, right? That's the value that is being stored. That's the hash value. Somebody else comes in and actually tries to log in, and they put in the 75. And they actually log into your account, because guess what? Both of these are hashing to the same spot. So even though they put a totally different password, the fact that they hash to the same spot, which means they give you the same hash, they might as well would have used your password, because the computer doesn't differentiate. It sees the same hash value. That's very bad. You don't want that to happen. It's another way you can crack the hash, but also it's just bad in general. Collisions are bad for not just for us, but in security as well. So you want that to be like highly, highly, highly unlikely to happen. Okay? Essentially, by doing that, you avoid somebody cracking your password with the wrong password. Because think about it. When somebody's brute force attacking you, if you have like 20 different words that would all match to the same as your real password, that's increasing your probability of actually the brute force attack hitting one of those, right? Imagine your password is like 20,000 letters. Okay, let's read this. Right? Your password is like 20 letters, 5 exclamation points or question, 5 special symbols, and then like 5 numbers. And you have this really good password. You're like, oh, I'm so secure. People told me that if my password is bigger than 10 characters, no one's going to ever crack it in my lifetime, etc., right? Guess what? The hash function that somebody made is so bad that if somebody was to write the word cat, it would literally hash to the same big, super, 100-character hash than your really big password. That's possible. It's actually quite possible, but unlikely. That, of course, is bad, because somebody doing a brute force attack, they try cat, logs in, they're probably going to be like, this guy actually used cat as his password or something, right? When in reality, you were using like some super complicated password, but it just happened things hash the same way. So that's actually what collision resistance is. So you can read about the birthday paradox on your own and other things, but I wanted to just give you that brief introduction into some of the important things that actually make a good hash function for both your usage and also for security purposes. So yeah, that's pretty much all I want to talk about with hashing, actually. Does anybody have any questions on this stuff? I guess looking at this, you might still be asking, like, why would you ever want to use open addressing when close addressing seems better? Open addressing can be good for cache performance and things like that, because you're keeping things in the actual table itself. So like, if you have a really good hash function, you're not going to have that many issues where things actually bunch up. So I suppose there you could kind of take advantage of it. Also, again, if you're really tight on space, if you hate pointers, I guess. Let's see. I think there's a table. with comparisons, but most of them I kind of talked about. That's pretty much it. Like I said, most of the time you're not really going to face it. You're going to separate chaining, close addressing is what you're going to see. That's what I said. Like, you know, if you're looking at a dictionary in Python and Java and things like that, they're going to be implemented using that method, close addressing with something like an AVL for the collision risk, for the collisions basically. So yeah. Well, since there are no questions, then that's the end of it. Remember, there's no class on Wednesday, and the test is next Monday. It'll be again from that 1 to 4 time range. What is our next programming assignment? So a worksheet has been released, or will be released at 5:30 p.m. today. I have it timed, so it releases after class ends. I think it's 5:30 when I put it. So you have to do that. And then after that, you are going to get some form of hashing assignment. I am still not 100% decided on how I'm going to do that. I was thinking, so to not use the same assignment I used last time, to make you implement a closed addressing hash table with ABL and store the Star Wars, the Sith fleet on it. So that's probably what I'm going to end up doing. I just haven't decided if I'm going to use an AVL, a heap, or a linked list for the chaining part. So, or maybe I'll leave it up to you. So you can expect that within a day or so. And that should be relatively simple because you just got to copy and paste your AVL assignment in there. And then just set up the hash part. And then maybe you can try exploring cool hash functions that you can use. Yes, that's the fun part. I want you to, because there's no way for me to emphasize the fact how hard to make a good hash function is than for you to just have to like try it out and see like, wow, this is actually harder than just, you know, I can't just do like mod 10 because it doesn't really work out, especially because those are those are names. So you're gonna have to figure out a way of doing some ASCII math. You know, you can try multiplying the characters together. You can try adding the characters together. You'll see that it's quite tricky actually to come up with a good hash function. So I think that's probably what I'll end up doing. I'll see. Maybe I'll do like, if you do a linked list, you get full points, but if you do an AVL, you get like extra points. I'll see. But yeah. Anyways, are there any other questions? When doing any sort of tree on the exam, do we have to rewrite the tree every time an element is inserted? So when you're doing AVL trees, I would like to see each individual rotation. So if it's a double rotation, I would like to see the double rotation. You only have to draw the subtree of the part that you're doing the rotation of, but then draw the tree after the rotation is done so that I can see the full tree. Copy and paste will be useful if you're using something like Paint or things like that. When you're doing things like building the tree from the traversals, I do want to see the tree as it's being built. Yeah, so at least once every time you add something to the tree. For traversals, you don't need to do that. You can just draw some arrows and show, and then of course show the output. For inserting into the tree, like I said, with ABL, you want to show the rotations, but if there's no rotation, then you can just kind of put those in. Like the first 3 or 4 numbers are not going to have rotations, so you can just draw it once. Yes, you will still get the extra time for uploading files. So it'll be the exact same schedule probably as the last test. So whatever the last test was, I think it was like from 1 to 5, or I don't remember what the times I used and the extra time. It'll be everything the same. Just the topics will be different this time. You should not expect to see anything from the first test in terms of topics. I try to fully focus it on the second stuff. You might see like questions about time complexity, but I mean, it will be related to like ABLs or heaps and things like that. Yes, as I just said like 5 seconds. I guess there's a delay. But yes, I mean, it's open notes, so I mean, you know, you should know what the time complexities of things is. I mean, I'm not going to ask you flat out like, what is the time complexity of this? Because you can just Google that. I will ask you more of like an analysis as to like why are ABLs log event, and then you can talk about like the height of the tree and things like that. But yes, if you guys have to go, then you can go. I'm gonna end the video soon, but when the questions end, I suppose. Will you get a worksheet? Probably not, but then you can probably ask a TA to give you some sort of examples of solutions to them so that you can see how they do it. But I mean, you have your program, so if you want to run and verify your ABL works, you can do that. Otherwise, on Canvas, I have a link to that one website that you can build the Avl tree there, so you can see the solution. So that's probably the best way, because I highly doubt that they'll actually grade them and return them to you, because they're due like 2 days before the test or something like that. I think it's due like Saturday night or Sunday night, and then the test is like Monday. So there's no way they're gonna get them graded. Anything else? I mean, I'll be available to talk if there's anything that comes up. I do highly encourage you to ask it publicly, though, so that I don't get the same questions. But you can always send me emails, too. My recommendation for the test is to practice the process of drawing and uploading and all of those things to have a good system. You did it for the first test, but like, you know, make sure everything is still functional there. And then historically, the hardest thing in the second test is Avl trees. The rotations get people all the time. So practice Avl trees by hand. Heaps, people usually tend to do okay on, as long as they know what they are. And building the tree from the traversal, people tend to do okay on. Traversals, most people do them right. It's more of like if they make a mistake kind of thing, which you can just double check. But ABLs is what historically is troublesome. So if there's anything you should practice, it's ABLs. And like I said, I might have a review video on the spring, because we had a different schedule. So check that out if you want. I'll try to find it and post a link on the description of the video. But all right then. Yep. Let me know if you guys have any questions, and good luck in the test, since I'm not gonna see you. But I'll be around. I can make the same technical test available, but I'll see. I'll see if I can make a practice one. Undetermined. I actually have to build a test first, but it should be about the same length. Probably about 1 question per topic. I mean, you can't do like 5 ABL questions. You would run out of time just on those. So, all right then. Well, any other questions, just let me know, okay? I know some people have to go to their classes and things like that. But I will keep you updated. I will like make an announcement once I actually have the test completed, like kind of like I did with the first test. So, cool. All right then. I'll see you guys later. Stay safe out there, and no class Wednesday, so don't show up on Wednesday. I mean, you're home anyway, so you'll be like, oh, okay. But, you know, still. You can sleep in if you're sleeping that long, I guess, or go, you know, have fun. Just be safe.